This is Dr. Smith, and you've got some WebAssign problems due on Sunday, and we haven't really had a chance to spend any time in class on these relative motion problems that you've got. So I want to sort of go over briefly how one approaches these kinds of things. Your book has some sections on those that are good as far as they go, but they don't really tell you what a good way to approach these kinds of problems is. So to explain what I'm doing, I want to set up a little sample here. So let's say we have a situation where we have a dad, the father of two small children, and he is going to be right here. He's going to be point D, and he's going to remain still, standing still with respect to the ground. So he's just standing still. He's got two kids named let's call one of them Alice, and let's say Alice runs. I'm going to do Alice in green. Alice runs this way. Let's say Alice runs this way, and at some later time, she's right there. Okay, in the same amount of time, let's say the other kid's name is Bobby. Bobby runs, let's say Bobby runs like that, and Bobby is right here at that same time later, okay? So, now what we want to do is talk about the position of these three people relative to each other. So, what I'm going to do here is show you how you'd plot out positions for these three things. So, or position vectors, and then I will explain what these mean, and then we'll go to velocities. Now, let's look at the position of Dad. Sorry, not the position of Dad. The position of Alice relative to Dad. Okay, so the position of Alice relative to Dad is a vector, and it's going to look roughly like that. Okay, so it's basically this green thing pointing in the same direction, same length. And what I'm going to call this vector is R, which is our standard position vector, and it's the position of Alice relative to Dad. Okay, so you put the first subscript. The first subscript is the subscript that refers to the thing it's the position of, and the second subscript is the thing the position is measured with respect to. So when you use this kind of notation, and I strongly recommend this because I'm going to show you how this works. It's got a little trick that makes it very easy to keep track of what belongs to what. You read this off the same way it's written. So you see the R vector and then AD. It's the position of A with respect to D. So position of A, now let's say A, which is Alice, but I think we can remember that, with respect to D. Okay, and that's how you would read it. Okay, position of A with respect to D. Okay, now what is the position of Bobby with respect to Dad? Well, that's going to be a vector called RBD, and let me see if I can draw that in more or less the right direction. That's pretty good. I've drawn worse vectors in my life. Okay, so this is the position of Bobby with respect to Dad, because Bobby is, south and then a little bit to the east. Okay, so that's about what that vector looks like. And that is the position of Bobby with respect to Dad. We write it the same way, B with respect to D. So these are both positions measured with respect to Dad. Here's the position of Alice. Here's the position of Bobby. Now, what I want to do, and let me put my D a little closer there. What I want to do is find the position of Alice. Now let's see, position of Alice with respect to Bobby. Okay, so one way to think of this is that these two are positions measured in a coordinate system that's centered on Dad. Okay, now how do we find the position of Alice in a coordinate system that's centered on Bobby? So when we say with respect to something, we're talking about measuring in a coordinate system centered on Bobby. So for this stuff up here, we're using a coordinate system centered on Dad, and you can imagine the x and y axes coming out from here. And now we want to find the position of Alice with respect to Bobby. using axes centered on Bobby. So first, I'm gonna sort of draw what we intuitively probably think that looks like, and in this case, our intuition is correct. Probably going. Let's see. Let's try that. I'm being so anal about the direction of these lines. Okay, so we're going to call this the position of Alice with respect to Bobby. And you can see that if you drew it in here, it would fit up. Okay, so if you allow for my horrible drawing skills, this is a pretty good representation. Okay, so sure, we can say this is what it would look like. How can we mathematically find that? Say we actually had, you know, these vectors. So now I'm actually going to draw an x and y coordinate system. Okay, and I'm going to say now Alice's position with respect to Dad is going to be, let's say she's, I don't know, let's call that 40 meters. Nah, that's just too far. 4 meters. 4.0 meters horizontally. Okay, and then 1.0 meters in our vertical direction. Okay, so that's Alice's position with respect to Dad. Bobby's position with respect to Dad. Again, I'm just making up numbers here. I'm going to say he's 10 over and 3 down. Or sorry, 1 over and 3 down. So 1.0 I hat now 1.1. I'm just going to keep these as 0.0s. 1.0 I hat minus 3.0 j hat meters. Okay, so that's the position of Bobby with respect to Dad. So now we want to find what the position of Alice with respect to Bobby is, and possibly you can sort of look at you know, look at the diagram and guess, you know, about what it would be. You can imagine, look, if Alice is 4 meters over from Dad, then you imagine it's probably about 4 horizontal, or sorry, 4 vertical grid lines here, right? And then if she's 10 meters up from Dad, there's something like that. And then Bobby is 30 meters down from Dad, so there's grid lines going down like that. And there's one more. So now I've probably drawn in a horrible little graph grid, but you can see how Alice is 1, 2, 3, 4 meters over and 1 meter up. Bobby is 1 meter over and 3 down. So you could, of course, just fill in and say, well, okay, so obviously Alice is going to be 4 meters up and 3 meters over from Bobby. Or, yeah, 4 meters up and 3 meters over. Or 3 over and 4 up. And so what I'm going to do here is write in that RAB, this is Alice's position with respect to Bobby, is 3.0 I hat plus 4.0 j hat meters. Okay, so all well and good. How can we express vector addition with these things? Or how can we express this as an operation on these guys? And I think if you look at it, it should be pretty clear that if you want to find, or if you want to make something, an equation that works, well, the easiest operation to set up with vectors in a triangle is addition. So you've got triangles coming out from D, so the position of A with respect to D is going to equal the sum here of these two, because you got one arrow pointing to B and one arrow pointing away from B. So you can see here that the addition of vectors RBD. So remember, this vector points to B from D. So it's the position of Bobby with respect to Dad plus the position of Alice with respect to Bobby. Okay, so now this is this red one, position of Alice with respect to Bobby, is equal to the position of Alice with respect to Dad. Okay, so if I just, I'm going to be super picky here and just underline all these in the colors that match up. Okay, so you can see, and this is stuff we've done, at least we sort of, you know, sniffed around at the edges of this kind of problem previously, but now I'm sort of trying to formalize it and show you what's going on here. Now the trick here is, first of all, if we want to actually find RAB symbolically, we can just solve this equation. Okay, so I'm going to take this equation and manipulate. This is supposed to be an arrow under. Jeez, that's horrible. And now I've just, let's see, is there a redo? Redo, maybe. Oh, well, whatever. Okay, so, I'm sorry, I suck. I mean, I'm horrible. I'm terrible. Pretend you didn't hear that word. Okay, so So if I want to find RAB, then obviously I just do my vector algebra here. RAB equals RAD minus RBD. So I'm just taking this guy and shuffling up to the right. That's all fine. But what I think is really most interesting to show here is that if you want to set these things up, what you can do, there's a little rule you can follow. So the rule is you've got three different positions you're working with. Okay, so three different relative positions you're working with. They are RAD, position of Alice with respect to Dad, RBD, position of Bobby with respect to Dad, and RAB, which is position of Alice with respect to Bobby. So to make a valid vector addition statement using these, what you do is you're going to have R something something plus R something something equals R something something. And the trick is that this subscript and this subscript have to be the same. Okay, so the second subscript on the first one, what the first position is measured with respect to, and the first subscript on the second one, what the second position is the position of, have to be the same. Okay, so same. Okay, now why? Let's just work this out in this particular example. So position of Alice with respect to Bobby. Sorry, we have this one, RAB, RBD, and RAD. Now, as it happens, if you're going to follow this rule and make this entry and this, this spot and this spot the same, then there's only going to be one possibility that works. And which one appears in both places? Well, here's B in the second slot, and here's B in the first slot. So that basically forces your choice. Because if you look at the other ones, feel free to pause the video and check, there are no other options. You have to have AB here, and you have to have BD here. There's no other choice, okay? And that leaves you with, we've already used BD, and we've already used AB, so now we have RAD is the last one to put in, and that's got to go in the last spot. And so what you'll see now, RAB plus RBD equals RAD. And in fact, if you look at this, this is the same as the relation we found earlier, just sort of by intuitively looking at these things, except that this and this are in opposite spots, but commutative property of addition, so that's all fine. So this is how you set up a valid addition statement. And I'll just write this again, R blank blank plus R blank blank equals R blank blank, and this spot and this spot have to be the same. So this one and this one have to be the same. And the interesting thing is this works also with velocities and with accelerations. So if these were velocities, say velocity of Alice with respect to Bobby, and velocity of Bobby with respect to Dad, and velocity of Alice with respect to Dad, you could do the same thing. That's, you know, that might seem like a bit of a stretch, but when you think about the changes going on in each of these, you'll realize they have to work out. What else was I going to say here? I think that sort of covers the basics of it, and this is how I recommend approaching these kinds of problems. I'm going to do a couple examples because, you know, it's easy, of course, to see the concept, but then it's a lot harder sometimes to apply it to a particular problem. So that will be the next video.